Okay, let's recap what we learned last week. We discussed about periodic signals, right? Periodic signals and the Fourier transform. When you see the periodic function, periodic signal, you always remember that periodic signal is related to the discrete signal on the other domain, right? So let's take a look at this table. In here, we see the continuous signals, and here we discrete time signals. But when you have a time, periodicity, you have a certain period of your time domain signal that appears to be a discrete in the frequency domain, right? And time period is, let's say, t. Then in the frequency domain, the per sample duration, that's going to be 1 over t, right? That's a 1 over t. So that's always the relationship when you have a periodic in time domain, discrete in frequency domain, or when you have a period in frequency domain, in time domain, it's going to be discrete. So this picture basically shows you a sampling of your original analog signal in time domain. Okay? Once you do sampling, then you have a time domain discrete signals, discrete samples. Therefore, your frequency domain will be now periodic. In this case, the period is 2 pi, right? Okay. And when you have a discrete and also periodic in time, then because this is periodic, you have a period in frequency domain. And because you have a period in time, you're going to have a discrete in frequency. So it's going to be periodic discrete, again periodic discrete. So that's typically the discrete time or DSP signals we always see. Okay? So that is the relationship of periodic signals. We discussed the energy signals and power signals last time, right? And energy signals is basically a signal with a finite signal energy. And this is an example of energy signal. You see that this goes to time, the time goes to infinite, but still your energy is only contained within this period. All the other time you have no energy. So therefore, you have only finite energy, right? And if you take the average energy over the whole period, or average power, that's going to be vanishing to 0. Okay? So in the energy signal, you have almost 0 average power, but you have a finite energy. When you see the power signal, for example, the power signal looks like this. So when you take the average of the whole signal over time, still you have a certain constant value, or you can say finite or finite mean signal power. But your energy is infinite because you have a signal infinite, right? So your energy is infinite. So it's a power signal has infinite signal energy. So that's the difference between the energy signal and power signals. We discussed a lot about the autocorrelation, right? And cross correlation. And that's very important in this course, actually. So one thing that you want to remember is when you talk about autocorrelation, just remember the radar example, right? Remember the radar? So you have a radar. In the radar, your purpose is to detect the airplane, something like that, right? To do that, what you're doing is you're transmitting xt, which is your own signal, right? And if there is airplane, then you're going to get the reflected signal back. And that reflected signal is exactly the same as your own signal, right? So what you're transmitting is xt. What you're going to receive as a reflection is, again, xt. But the difference is that your reflection comes a little bit later in time. So there's a time difference. Right? You're transmitting back, so there's a time difference. But that time difference is not part of this autocorrelation. That difference tells you how far it is, right? You get reflection in 1 second or maybe 10 seconds. That means the airplane is close or distance away. So that is a distance. So that's not important here. What is important in delta is when you slide, you have your own xt, and you receive the reflected signal, and when you slide, right? When you slide, this is same as a convolution. Remember, right? And what is the difference between convolution and this one? This is flipped. Why do you flip? Because in the original convolution, let's say you want to convolute xt with xt. You want to do convolution, xt with xt, same thing. Then in order to do convolution, what you do is that for the second one, which is xt again, you flipped it, right? Left to right, and then slide. So when you slide, you have your own xt, and the second one, it's the same xt, but you flipped. So when you slide, basically you are actually calculating correlation with the original version and flipped version. That's a convolution, right? Remember that? So in autocorrelation, what you do is that you are basically doing convolution with xt and x minus t. So, and then you do convolution. When you do that, so second one is x minus t. Remember that? So autocorrelation is basically xt convoluted with the minus xt. So when you do this, right? When you do convolution, the second one is actually x minus t. So you have your own xt. For example, like this, that's your xt. You want to do convolution with x minus t, which is flipped version. Now then, when you do convolution, you are going to flip this one, second. The second one you are going to flip, right? So you're going to flip it and then slide. So when you slide, it actually matches. It has the same shape, right? It matches exactly. So since the convolution flips it, you're going to flip it one more time. So it's going to be flipped by this one, and the flipping again with the convolution, by the convolution. So it actually comes back to your own, and then slide. So therefore, when you slide, it basically matches exactly when the delta equal to 0. So this delta is not the delay between your transmit and reflection signal. That's not delta, right? Delta is the difference, time difference between these two when you do convolution, when you do correlation calculation. Okay, that's the delta. So delta equal to 0 means that when you slide like a convolution, this one matches exactly like this. Everything matches. That's delta equal to 0. Okay? So that is autocorrelation. So typically when you calculate the autocorrelation, since the second one is sliding, right? Sliding, it always like autocorrelation value, initially it's 0 because there's no overlap. And when you have a little bit of overlap, it starts to increase. And then it exactly matches. That's a delta equals 0. Then it always get a peak. And then it's keep going. Then it's going out, right? It's fading out like that. Then it goes down like that. Eventually it passes. It becomes 0 again, right? So always you get this kind of figure in autocorrelation. You always get going up and peak and then going down. And this peak point is where you get the delta equal to 0 when you get exact match. So that's autocorrelation function. When delta equals 0, which is the peak, the value is exactly the same as your original energy in the signal. Right? So that's the delta equal to 0. Cross correlation is similar, but the difference is that in cross correlation, you are calculating the correlation or similarity between two different signals. In the previous autocorrelation, you are trying to look at the correlation or similarity between your own signal. You just slide with your own signal. But in this case, you are trying to calculate the correlation of two different signals. You have xt, you have another signal, yt, and you are sliding. And see how close this is, how similar these two are. If those two signals are close or similar, then you will get some value. But if these two different signals are completely different or orthogonal, then since these two are orthogonal, that means no similarity, no correlation. That means you're going to get 0. Okay? So this test, cross-correlation test, will tell you what is the correlation between these two different signals. So if you get a 0, that means these two signals are perfectly orthogonal. Typically, that means good, right? Because you want to design a orthogonal signals or different signals. There are many reasons why you want to do that. Right? When you do the system design later, then sometimes you are trying to design a orthogonal signals. And how to do that? You know, based on this, you can measure the correlation. And the correlation becomes 0, that means orthogonal. So this is a way to do it. And when you take the tau equal to 0, that means these two signals match in time. Right? When tau equal to 0, still that means xt is right here and yt is sliding, and both are match, tau equal to 0, then you get 0. That means orthogonal. If both are misaligned, of course you 0, right? Because here xt is here, yt is there, of course you get 0. That's not orthogonal, right? You match it, perfectly match in time, tau equal to 0, you get value 0. That means orthogonal. Okay? So that's a cross correlation. As I said earlier, typically autocorrelation, you want to get a high value. Okay? Why? Because autocorrelation peak, this is going to be the peak value. When tau equal to 0 means the perfectly match, you get this value. This value is going to be your peak value. Peak value, right? This value. You want to have a high peak value because that's going to be your energy. Right? It's the energy of the signal. You want to have highest energy in your signal, typically, right? You want that's part of your design. So your autocorrelation value wants to be high as possible, but cross correlation value typically you want to make it low as possible. Okay, that's a typical way of designing signal. Later, probably much later, we may have a chance to design xt and yt later. Right? When you do system design and things like that. In that case, typically you want to have high autocorrelation and low cross correlation. So the difference between autocorrelation peak, the autocorrelation and cross correlation to be very large. That's a good signal. Good signal design. Okay. So that's the meaning of cross correlation, autocorrelation. So remember, this is not difficult. When you look at this equation, it looks like difficult, but think about correlation, convolution. Okay, this is actually same as convolution. The only difference is that this is flipped, and you are doing convolution of your own signal, xt and x. This complex conjugate, that's not important. The reason you have complex conjugate is because this xt is a complex value, complex signal. Typically, you don't see complex signal. In the real world, it's always real. But when you see complex signal, you want to have a complex conjugate, and the important thing is you flipped, and you are doing convolution with your own signal, flipped version. In the cross correlation, you are doing again convolution, but in the second one is a different signal. This one also you flipped, right? So it's going to be y minus t. You do convolution. So it's the same as convolution, simply speaking, right? So not that difficult. Okay, today, first thing we want to discuss is the energy spectral density and power spectral density. Okay? Simply speaking, energy spectral density is related to the energy signal, and power spectral density is regarding the power signal, right? We just discussed the energy signal and power signal, right? So what we want to understand is spectral density. What is a spectral density? Okay? Now, to do that, let's think about a very simple scenario, okay? So in the last week, we already looked at a relationship between the time domain signal and the frequency domain. So changing from time to frequency or converting the time domain signal to frequency domain, it's an analysis function or Fourier transform. Now the question is, let's say here, what is this one? I mean, is this, let's say this is value 1. Then what is this 1? Is this amplitude or is this power? What is this? We know that this is time domain. We know this is frequency domain. We know that. But what is it showing here? What is it? Typically, when we see the time domain signal, that means this is amplitude. Typically, right? Generally, we see that this is amplitude. This is time domain signal. And time domain signal goes up and down, like that. So that's a time domain signal, just amplitude. Amplitude can be positive, negative, going up and down like that. That's typically what we see. Take the Fourier transform. We see the frequency domain. This one, again, is just a frequency component, right? How much frequency is in there? Something like that. Okay. Now, what we want to do is that we just learned the autocorrelation, right? Autocorrelation. As we discussed, in autocorrelation, the x-axis is tau. Autocorrelation is always use the axis tau. Okay, tau. And autocorrelation goes up and down, something like this, right? When tau equal to 0, you have a peak value. So still, this is a time domain. This is not exactly same time domain as this one, because this is a time domain like a t, but here it's not t time domain. This is tau. Tau is not exactly time, not the same time this one. Tau is actually time offset, right? One signal is here, another signal is sliding, and how much time difference you have. How much is offset? That's a tau, right? So this autocorrelation is always a relative time difference. You have one signal, okay, one signal. Let's say you have this signal, time, x1t. You have another signal, x2t. And x2t is actually same signal, but time difference. Let's say the same time, same signal, looks like the same, but we have time difference. That's a tau. Okay? So it doesn't matter t. T is actual time domain signal, time domain t, but that's not part of the autocorrelation. What the autocorrelation has is the time offset. Okay? One is here, one time domain signal is here, the other time domain is somewhere here. So you have a difference. Time domain difference. That's tau. And autocorrelation, as I said, is the relationship between these two time domain signals. So your axis is a tau, not t. But still it's a time domain concept. This is Fourier transform. Now let's think about a Fourier transform of this autocorrelation. This is Rx tau. That's autocorrelation. Okay. Now let's take a Fourier transform. Then what do you have? This is autocorrelation, still in time domain. Still we are in time domain. You are taking the Fourier transform of autocorrelation. The earlier here, we are looking at xt. So you are getting xf. You are taking the Fourier transform of your time domain signal xt. So you are going to get the xf, which is the frequency domain representation of your signal. Here, we are looking at the autocorrelation of your xt. Right? This is not xt. This is autocorrelation of xt. Now you want to take a Fourier transform of autocorrelation. What do you get? That's the spectral density. So what the spectral density tells you, something like this, just example. Okay, and here we say like that. Simply speaking, this one, autocorrelation. Okay, autocorrelation is like a square. Is it square, right? Because think about the autocorrelation. It is a, going back to the previous slide, when you look at the autocorrelation function, it's kind of square. I'm saying it's kind of. Think about the concept. I'm just giving you a simple way to understand. Here, autocorrelation is an integration of xt and another xt. So it's kind of you are multiplying xt 2 times, like a square, kind of, right? So when you have xt and multiplying xt again, like this, right? Think about this one. This is the example. This is the case where the tau equal to 0. When tau equal to 0, this is 0, then this is going to be x squared. And what is a square? When you take the square and integration, that's going to be your energy. So autocorrelation is somehow related to your energy, not the amplitude. So that's what I'm trying to say. Here in the upper figure, this is not the energy. This is your amplitude, just the amplitude, high, low, or it can be negative, right? Going up and down, sometimes it can go negative. This is just simple amplitude. Whereas in autocorrelation, what you are seeing is somehow is energy because it's square. Okay? So now the y-axis is different. It looks like a time domain, looks like a frequency domain, but that's different, very different. Amplitude, this is the power or energy. So now, since this is the energy, you are taking the Fourier transform. What you are seeing is, again, energy in frequency domain. So what we call that as spectral density or power energy spectral density. For energy signal, we see energy spectral density. What is a spectral? Spectral means in frequency domain. In frequency domain. Density, what is the density? Density is a unit power, the power within the unit frequency. That's density. So the spectral density, energy spectral density means that the y-axis here is going to be your energy or power, meaning square. Here this is square. Again, this is square. This is not square. That's the main difference. To me, this is easy to understand. I don't know if that's easy, but otherwise, if you look at a book, textbook, the book will say, when you take the autocorrelation and Fourier transform, you will see the spectral efficiency, spectral density. But it doesn't really easy to understand, right? It's not easy to understand. So what I'm trying to tell you is, think about a square in here, down here, right? Down here. And up here, this is not square. The autocorrelation, take a Fourier transform, now the spectral density. Okay, spectral density. And in spectral density here, this is a power. Again, autocorrelation. So you never get a negative, right? Because you square, you never get negative value. Always get positive. So always going up and down. Here again, power spectral density is always positive. You never see the negative, right? Because it's energy density or power density. So here, let's read it here. The energy spectral density is non-negative, meaning always 0 or positive. Real value quantity for all frequency. See that this one, right? XF, this absolute value squared, that means energy. Okay, energy. This one, it shows some relationship, but this relationship basically tells you the relationship between these two. Just a mathematical way of telling you. Here we have autocorrelation, Rx tau. autocorrelation, you take a Fourier transform, right? Fourier transform, then you get spectral density. This one, inverse. You have a Fourier, the spectral density, inverse Fourier transform, you get the autocorrelation back. Okay? So that's simply a relationship between these two. I know that it's not easy to understand right now, but later, I think we have probably a chance to talk about this one more time. Later, when we talk about noise, things like that, we'll probably look at it one more time. Okay? So just remember the relationship between these two. In here, in the spectral density, same as previously discussed. When you take the autocorrelation, when you take the area of a whole autocorrelation, that's going to be same as the spectral density when the f equal to 0. That means it's basically the same as this relationship, right? Remember that in the original Fourier transform relationship, you are taking the integral of a whole area. The whole area is same as this value, right? Same thing here. You added whole thing. That's what they mean, right? Integration of the whole thing is same as this value. It's same, basically. It's nothing new. Okay, nothing new. Similarly, here you are adding all these things, integrating all these things. That's going to be same as this one, right? So nothing new, same as before. So that's what you're seeing here, these two. Power spectral density, it's basically the same. What we looked at in the previous slide was energy spectral density. Same concept in power spectral density. The only difference is that in power spectral density, you are taking minus t to t, and eventually t goes to infinite. So it's basically the same thing. The difference is that that's for energy signal, this is for power signal, but pretty much the same. Typically, we more often use this word, power spectral density, because we always see power signal. Later, when you look at the communication system, we always see a power signal, right? Your signal always goes like a sinusoidal. You never see like you have only energy at this time and 0. You never see that, right? You always see like a sinusoidal signal that goes forever. So you always get power signal. Therefore, you always see power spectral density. Okay, so power spectral density is same as energy spectral density, and the power spectral density is the Fourier transform of autocorrelation. Now, let me ask you one question then. Let's say, what is the perfect autocorrelation? No, that's the peak value. That's the condition when you get a peak value. What is the shape of your autocorrelation depends on your xt. So maybe my xt looks like this, or maybe my xt looks like this, right? Think about radar. I can transmit my xt, but my xt, I can design it. I can design this. I can transmit this signal, whatever signal I can transmit. So depending on the xt, your autocorrelation, okay, looks different. So what would be the perfect autocorrelation? Perfect means a little bit different, but in some cases, right? In some cases, in the very, very ideal scenario, you can see this autocorrelation. What is this autocorrelation? This means that you are sliding with your own. And even though you have overlap, still you get 0. Let's say that basically means that you have your xt. Your xt looks like this. Looks like this. Just the example, okay? And then you are doing correlation. So you have a little bit of tau. You have this, okay? But what is the correlation between these two? 0. because you have a tau equal to 1, let's say still 0, right? This is 1. Only when you have a perfect match, meaning tau equal to 0, you have some value. When you have a perfect match, only then you have some value. You have a still mismatch, a little bit mismatch, correlation is 0. That's what they mean, right? That's a perfect scenario. That's very, very ideal scenario. That's very perfect. Perfect, really. Ideal, right? Very ideal. In that case, okay, we'll discuss this one later when we talk about noise, right? Later, after midterm, I think we probably talk about noise at that time. Noise has this property. Okay, we'll talk about this later when you talk about noise. But now think about it. When you have in time domain, you have this signal. Then take a Fourier transform. Then what do you have in frequency domain? You have an impulse in time. So in frequency, what do you have? What do you have? Huh? Impulse in time, take a Fourier transform, then what do you have in frequency? Flat. Flat, right? So when you have this autocorrelation function, of course this is ideal only, then you'll get this power spectral density. What does that mean? That means you have equal power for all the frequency. That's what they mean, right? That's what they mean. All the frequencies, you have exactly equal power. Right? That's what they mean. Let me ask you a question. We see that white light, right? Natural light. White light. You put it into the prism. Then prism will show you all of the frequency component of this white signal. Right? Then you see rainbow color, all different colors. What is the power of all these different colors? Each color is a different frequency. You know that, right? Yeah, red color and blue color and purple color, each color has a different frequency. But we want to see that the prism will show you or take a Fourier transform of the white light and show you all these different frequency or colors. What's the power for each color? Or what's the power for each frequency? It's the same, right? All the color has the same power. If the one color has a higher power than another color, then you're not going to get white color. So white color means all of the different colors or different frequency have the same power. So that's exactly like this. So when you look at this one as a color point of view, this is a frequency, by the way, right? This is spectral density. But when you look at this one from the color point of view, this is white color. Why? Because all the different frequency, all the different colors have the same equal power, so that means white. Some of you heard about additive white Gaussian noise, right? Yes. Have you heard about that? Yes. Yeah, so we'll talk about it in detail later, but additive white Gaussian noise, that's called AWGN. So why is it white? Noise is white? What does that mean? White noise? Then what about yellow noise or blue noise? What is white? What does it mean by white? This is not actually color, right? Because you never have a color in noise. There's no blue, there's no red noise. Only white noise. What does that mean? That means this one. Your noise, you have a noise, but your noise have all the equal power over the whole frequency. So that's the characteristic of AWGN. We'll talk about that later, okay? But that's one of the purpose that you see the power spectral density. That's exactly power spectral density picture. So this is a power. This is a frequency domain. That's why we see spectral. Spectral means frequency domain. So we are looking at frequency domain, but y-axis here, this is actually a power. So this is power spectral frequency density. Okay? And that's some relationship with autocorrelation, okay, by Fourier transform. Okay, we'll come back there later. Okay, now it's time to think about our main topic. So that's modulation. And today we are going to briefly introduce some basic or definition of modulation. So what is the modulation? Very simple. Okay, everything needs to be simple. Okay, modulation. Look at this red one. Information bearing signal. What does that mean? Your signal has the information. Your information bearing means your signal is carrying information. Okay? That's the information bearing signal. What does that mean? That means our signal. We are talking about communication. Okay? So I want to deliver my message to him. So I have my message. That's this one. That's information, right? I have my own message. I want to deliver my message to him. So now the question is, in communication, I have my message. I want to deliver this message to him. Okay? What is the best way? What is the most efficient way of delivering my message to him? Or delivering my package to him? That's the whole communication. Simple as that. But think about this way. Let's say, let me just put in an example. Let's say my friend is in Canada. Okay? I want to send my package, small package, to my friend in Canada. What is the best way? Maybe there are many ways. Maybe you can run it with a package and swim. Maybe that's not a good way, right? Or what is another way? Maybe you can put it into the airplane. That's the best way, I guess, right? Or there are many, many ways. So now the thing is, airplane, what is the airplane? Airplane only delivers your package. So what that means is I have my package, and my package, I put it into the airplane. Then airplane simply delivers it and give it to him, my friend, right? So this airplane is simply a carrier. We call it a carrier, right? We call airplane, things like that, as a carrier. I'm saying in general, not in our class, but generally you call the airplane as a carrier. When you go to airplane, airport, you always see carrier. So carrier basically means that carrier is not part of your information. Your information is information bearing signal, your package. But in order to deliver your message efficiently, you are using carrier. And the carrier can be an airplane, or carrier can be a bus, anything, right? Train, anything. Any of those things can be carrier. Same thing here. I have my own signal. I want to deliver my signal to the receiver. I have a transmitter. There's a receiver somewhere, and I want to deliver my information to the receiver. But I cannot deliver as it is. I have to use a carrier. And this carrier, like an airplane, carrier simply put my information into the carrier, then carrier keep it and run. And then deliver to him, and carrier no longer is useful. Carrier is only useful to bring here to there. Carrier itself is not a message. Does it make sense? So we'll look at that in the next slide. We have many different modulations. Throughout this course, we'll talk about many, many different modulations. But in continuous wave modulation, or we can say analog modulation, we can think about two different ones. Actually, one more, but generally we have two. One is amplitude modulation. We'll talk about this one today. Second is a frequency modulation or phase modulation. Those two are in the same category. So we have two different things. You heard about these things, right? When you take a look at the radio, you can see AM radio. This is AM. Amplitude modulation, we call this AM. So your original AM radio, like old style AM radio, they use amplitude modulation. You heard about FM radio, right? Yeah. And you know the FM radio probably is better than AM. And we'll see why. But anyway, this is FM. And here is AM. Okay, those are some analog modulation, continuous wave. Now in the AM modulation, when you look at it more detail of AM modulation, we see 4 different things. One is traditional, old style amplitude modulation. We'll talk about this today. Second thing is double sideband suppressed carrier. We call that as a DSB, double sideband DSB. Okay, we'll talk about later, maybe weeks later. And the third one is a single sideband. It's called SSB. Okay, and last thing is a vestigial sideband VSB. This is the one that is used for TV. Okay, TV station, all the way, not digital TV, analog TV. Okay, analog TV all the way, they use a VSB. But VSB is just an extension of these things. So we are not going to look at the detail of VSB, but we're going to look at the details, DSB and SSB, until midterm. Okay, today we're going to look at the simple one. Okay. Here's what we have. Okay, let me draw a simple figure about the thing that I just said. I have a package. Anyway, so this is a package. I want to deliver this package to my friend. And I want to put this package, and I like to call that as MT because this is my message. Okay, this is my packet. I want to deliver this message. Put it into carrier. I want to put it into the carrier. And this carrier flies and eventually arrive somewhere here and then bring it to receiver. And right here, what I receive is RT. And this carrier, I like to call as a CT because this is carrier. And this is RT because I like to call this RT because this is received signal. So this is exactly the same concept in communication, in our communication. We have a message. That's the message, my message. I want to deliver my message, original message. That's information. I cannot send the message just it is, okay? Because if I just send the message, let's say my voice, I want to talk to my friend. If he's right here, then I can talk and he can listen. But let's say my friend is in somewhere else, some other that building, then he cannot hear me, right? So I cannot just say my message cannot be delivered to the receiver. So what I need to do is that I need to put my message into the carrier, and then this carrier will deliver this message for me. Eventually, this carrier will be dropped somewhere here. You don't, from here to here is a carrier, right? You don't need the carrier right here at this point. So eventually you recover the message back. So that's the way. Now in the same way, in the communication, in our modulation, this carrier, in our amplitude modulation, in this carrier looks like this. We are not using airplane, right? We are using this one. That's going to be our carrier. Okay? This is our carrier. So this is the carrier that we are using. this is simply a sinusoidal signal or cosine signal. So that's our carrier. Very simple. Why do you want to use this one as a carrier? Think about this way. In this case, right, we are using airplane because this airplane can fly and go from here to here very fast. But let's say this is our air, right? Our channel is air. But now, just think about that. Our environment is underwater. You cannot use airplane, right? In underwater, maybe you have to use submarine, something like that, right? So depending on which environment you have, depending on the channel, you can use a different carrier. Okay? Different carrier. Same here. We are using cosine sinusoidal carrier. Why is that? Yes. You learned the electromagnetic wave, right? EM. This is electromagnetic wave. And we know that in the air, like this, in the air, electromagnetic wave, sine wave, is the most efficient way of delivering the signal. Okay? It's electromagnetic wave is the most efficient way or most efficient signal to penetrate in the air. Okay? So in our channel, the medium is air. And the electromagnetic wave or cosine sinusoidal function is the best one to use. That's why we use this one. And this carrier has its own amplitude, AC. This AC is the amplitude of the sinusoidal signal. And it has its own frequency, FC. FC we call as a carrier frequency. Carrier frequency. Since this is a carrier, of course you want to call this one as a carrier frequency. Okay? So you have a carrier. This is a carrier like an airplane, and carrier has its own amplitude. Carrier has its own frequency. So carrier frequency, carrier amplitude. But this is what the carrier looks like for us. Okay. Here is the amplitude modulated signal. So what we do is that using this carrier, we want to use this message and put this message into the carrier. Like put this message into the airplane. Now our carrier looks like this. So we want to put the message into the carrier. So how do you combine this message and carrier? There are many ways, many ways. So each way is a different modulation. An amplitude modulated signal, in this signal, you put the message with the carrier this way. Okay, I'll tell you what that means. Simply speaking, that S means send. So right here, right? S means send. S. I have my own message, MT. And let's say, as an example, my message looks like this. Just an example, right? I have my own message. I cannot just transmit message, it is. I need to put this message into the carrier. So I have to use carrier, and our carrier looks like this. And what you need to do is you need to multiply these two. You need to do multiplication. But in amplitude modulation, what you need to do actually is Ka, right? Ka. You want to make a signal like this, St. When you look at this, right? This part is carrier. And this is message. And we have a little bit more here. I'll tell you why we have this one. But the basic concept is you have your own message, right? And you have a carrier, multiply these two. That's the basic concept. Okay? This multiplication is same as you put your message into the airplane, like that, right? And that's going to be ST. ST is what you are transmitting into the antenna. Okay? This signal goes into the antenna, transmitting to the air. Okay? So simply message multiplied by the carrier. So that's how you load message into the carrier. Okay? Simple, like that. When you take a picture, block diagram, simply it's like this, right? So simply multiplication of these two. Later, weeks later, when we talk about DSB, double sideband, you will see this picture. Okay? Not now. We are looking at this one right now, but you'll see this picture later. But in this case, in amplitude modulation, actually we have something more, 1 plus Ka. Okay? We have something more here, not exactly MT times CT. We have something more here. So I'll tell you what that means. Ka is just a gain. So sometimes you put the Ka in order to make it small or make it large. So it's like a gain. We call that as a gain. You can make this MT smaller or bigger. But this is a constant value. Maybe it's a 1 over 2, or maybe 1 over 3, or maybe 2. It's a constant. So it does not change the shape. Your MT looks like this. And let's say your Ka, as an example, let's say this is a half. Then right here, you get the same thing, but a little bit smaller one. Because you multiply half, it becomes half. Right? Or if you multiply 2, it becomes double. Right? But the same thing, same shape. That's Ka. Plus 1. You have a plus 1. Okay. What is the plus 1? Like what is 1? We are always looking at the frequency. We are talking about frequency always. Constant value is a DC. It's a frequency 0, right? It's called a DC component. We call this a DC component. Now we are adding DC component. So when you add a plus 1, now let's see what happens. Now we want to add a plus 1. Plus 1. Right here, when you add a plus 1, then what happens? Let's say you have MT, original MT, multiply Ka. Ka, let's say, is a half, 1 over 2. Then right here, it looks like this. Make it a little bit smaller. Now, on top of that, you are adding plus 1. What happened here? This one plus 1, simply. So this is empty. So what that means is everything goes up by 1. So now it goes up like this. It was like this before, but now it goes up by 1. Okay? Because you are adding 1, so it goes up. So originally it was like this. And now you do a +1, this one goes up. It doesn't change. It doesn't change the shape. The shape signal looks the same. It only goes up. We call this lift that up, right? Lift the signal up. Why do you want to do that? I'll tell you why. When you lift that up, one thing, and why we do that is because that sometimes in the MT you have negative, right? Because in the signal sometimes goes positive, negative, goes up and down. But by adding +1, you can make all the signal always positive. So that's why we want to do +1. You want to lift that up so that you want to have everything positive. So that's why we want to do that. So right here, you see this signal, and now this signal is positive all the time. Positive. In the previously, sometimes negative, right? But now, when you add the +1, it's always positive. Once you make a positive, you are multiplying carrier, which is this part. Then now you get this, ST. Right? Okay, now the question. Let's say you have this signal multiplied by a carrier, and typically this carrier has a carrier frequency FC, right? But this carrier frequency is much, much higher, very fast, higher frequency. So when you draw this picture, this is simply cosine. So that cosine is a high frequency. High frequency means your wavelength is small, right? So your frequency looks like that kind of frequency. That's a carrier, CT. This is a 1 plus Ka MT. So now you're multiplying this one with the CT, then what happened? Just simply multiplication. Then what happened? You are just put this one here. That's what happened. This one is this part. This picture is 1 plus KMT. Here, you are multiplying carrier. This carrier looks like this. FC, the carrier frequency is always very high frequency, very high. So therefore, you have a very fast fluctuating sinusoidal signal. So you multiply this one with this one, then you're going to get this. Okay? This is ST. And that is what we transmit over there by antenna. Okay, that's what we transmit. This is an AM signal. AM. Okay? Okay, so this is a ST right here. That's what we transmit over there. And I'll tell you that if you don't do a DC, this is a DC. You are adding DC, right? So the next slide here shows you that, let's say you are not adding DC. If you don't add the DC and just multiply cosine, in that case, what happens is, let's say this is the original signal MT. And by multiplying Ka, maybe you shrink a little bit. Still, you have a negative. Because you didn't do add AC, DC, you still have a negative value. When you have a negative value, and multiply the carrier, now what happened? Think about this one, multiply this one. What happened? This cosine is multiplied here. When you have it here, let's say it's 0.2, 0.5, then here you multiply 0.2, it becomes smaller, 0.5 becomes a little bit larger, things like this, right? And right here you have a minus. You multiply minus 0.3, then here you multiply minus 0.3, now it's flipped. So something like you have a cosine, and suddenly you become minus cosine, and again cosine, plus cosine, something like that, right? So your carrier now, the sign is now positive, negative, positive, negative. It becomes like this. You have a positive, and suddenly it becomes negative, and again positive. It's hard to see here, right? But that's what happened. If you don't do +1, then this is what you see. Okay, that's what you see. And what's the problem about this one? Yes. When you do this, right, the problem is that we cannot use envelope detector. And I'll tell you later what that means. But simply speaking, it's hard to receive, hard to detect. Eventually, right, eventually what we want to do is that we receive these things, because this is what you transmit over the air, like this one. This is what you transmit over the air, right? And in the receiver, what you do is you receive this. And eventually you need to recover this back to this, right? I want to get this one. I don't want to get this, right? This. This is simply carrier. You multiply when you transmit, and at the receiver, eventually you remove it. Because in the airplane, think about that. My package goes in the airplane. I put my message into airplane, and airplane flies, and in the receiver, eventually you take off the airplane. You don't need the airplane anymore. You take a message back, right? So eventually the carrier will be gone at the receiver. So eventually you receive this and then recover this back eventually, right? So I'll tell you why. And the envelope detector, in this case, you cannot use envelope detector. That's why. And we'll talk about that in the next time.